Hi, I'm Jonathan. I am giving you guys an update on my embedded systems project for school. I'm currently going to school to be an electrical engineer, but in the meantime, I want to help however I can. So my project is having to do with the Enabling the Future, or Enable, Phoenix version 2 3D printed prosthetic hand. It's cable actuated. I don't have the whole thing assembled currently because I'm working on bits. What I intend to do with this is leave it cable. The cables will still open and close the hand, but I'm actually adding a motor and some sensors to it. I am using the MyAware muscle sensor. You can see, get there, going right here. Sorry, can't really see my camera when I'm doing that. And I'm having to create my own brackets and do some other things. What I'm doing is not new by any means, but what is a bit different is I am going to make my final version fully accessible by the end of the year to everyone. I'm donating all of my SolidWorks, all of my models, my code, and everything. I am keeping my parts list total build cost under $100. Most people that are doing this are using servo motors or linear actuators or custom made motors and things like that. That's all fine, but they're still a bit more costly. I'm trying to keep as minimal as possible. I'm also trying to make my package size, total size for the electronics and whatnot, as small as possible. So I've got some design challenges. What I've done so far is redesign the standard gauntlet. Now I have this is not scaled up at all. This was printed about a year ago on my school's 3D printer. It's not great quality, but it's good enough for prototyping for this project. So I've redesigned the cable carriage where the cable's attached. Sorry, I got my kids. They love this thing. Shh, please. Alright, so I've redesigned the cable carriage to allow this threaded shaft from this Pololu micro metal gearbox motor with a threaded shaft. This on Amazon is only, I think, like $6 or $8. But I've tested it in the lab to see how much force it takes to pull the cables and actuate the fingers, and how much this thing can do, and at what power and all that good stuff. And I've determined that it is sufficient to do what I need. The added advantage of having this threaded shaft is that, the added advantage of having this threaded shaft means that I can hold my hand closed with no power applied. That's just a property of using like a worm gear, which is what I'm kind of treating this as. So you see my two little metal nuts in here. I'm using two of them for redundancy and added surface area for the threads, because these threads are quite fine. So the motor rotates and it pulls this guy back on that, and in turn also pulls the cables. Now I'm redesigning the gauntlet. As you can see on my SolidWorks model right here, I've redesigned the gauntlet to allow for my motor to be mounted on a very sturdy, well secured mount in line with this guy, and this will basically be able to just slide back and forth like that. For those of you that aren't familiar with the MyAware muscle sensor, you can see I have the 3 probes attached. This is a ground strap, and then my 2 muscle sensor probes, using these little 3M dudes. My final design is I'm trying to get away from using these stick-on reusable, or not reusable, these stick-on disposable stickers, probes, because they just add to the cost of use. You have to change them out every day. They fall off if you sweat and all that other stuff. So I'll be looking into some form of sleeve that I can attach the cables to, and the sleeve will have the sensors or the probes embedded in it in the correct position, or something. I haven't gotten that far yet. But yeah, so the MyAware muscle sensor. This is about the most expensive component, around $37 on adafruit.com. Running my cables for this uses electromyography, EMG. I have it hooked up to my analog discovery sensor module. This basically provides me a signal generator, oscilloscope, logic level sensor. It gives me a whole host of electronics tools to use within this software. So you guys don't have to have this. This is just what I'm using to help me develop my product. So here we go. So when I flex my muscle, you can see it goes up and down. A signal is generated or sensed by the device. And using that signal, I will tell this MSP430 microcontroller. This is the G2553 model from Texas Instruments. You can get these on Amazon for around $4 or $5. These are super cheap, fairly simple to work with, provided you know how to program in C++. My final design, I will be looking into having some way of programming this that won't require a whole bunch of software or much in the way of skill level or any kind of coding knowledge whatsoever. I'm trying to make this as simple as possible. I haven't fleshed out all the details because that's not necessarily within the scope of my project for this class. At the end of this semester, I will be continuing this project to fully flesh out everything and then create an Instructables on the awesome website Instructables.com to show everybody how to do this or how to make this thing. And it'll include a full shopping list, links to all the Amazon parts. Sorry, so I had to take care of my kids. So part of being a dad and a student at the same time is having to figure out a good mesh between work and family and whatnot. That's okay. All part of the process. So yeah, there we go. I will need, for this class project, I think I'll have to do a little bit of collaboration with some people that know how to utilize SCAD to help me edit my SolidWorks models so that they can be scaled up and down uniformly, while making sure that the motor and the track and everything stays where it's supposed to be and does what it needs to do. The coding I'll be doing all myself. It's fairly straightforward. So there we go. Don't have to change the world to help people. You just got to light one candle. All right. So if you like this, if this interests you, let me know. If you think you can help out, let me know. I will be needing people this summer, most likely, to help me finalize or help me flesh out all this and the workload that's going to be done, because I will have to do a full write-up on it as well as the instructions. To make sure that I take care of everything that needs to be taken care of. That's why engineers work in teams typically. We help prop each other up. So, all right, there we are.